Hey everyone, have you ever noticed your phone or laptop charger getting warm after it's been plugged in for a while? Or wondered why some light bulbs glow brighter than others even when plugged into the same outlet? The secret behind these everyday observations is a fundamental concept in electricity called resistance. So, what exactly is electrical resistance? Imagine electricity as water flowing through a pipe. A nice, wide, clean pipe lets water flow easily. But what if the pipe is narrow or filled with rocks and gunk? The water has to work much harder to get through, right? That's resistance in a nutshell. It's the opposition to the flow of electric current. In an electrical circuit, electrons are the water, and the material they flow through is the pipe. Every material has some level of electrical resistance. We can group materials into two main categories based on this property: conductors and insulators. Conductors like copper, silver and gold are like those wide, clean pipes. They have very low resistance, allowing electrons to flow through them with ease. This is why we use copper for the wires in our homes and electronics. They efficiently carry electricity from one point to another without losing much energy. On the other hand, we have insulators, materials like rubber, plastic, glass, and wood are the electrical equivalent of a pipe that's completely blocked. They have extremely high resistance, making it almost impossible for electric current to pass through. This property is incredibly useful and important for our safety. The plastic coating around a copper wire is an insulator. It keeps the electricity safely inside the wire and prevents us from getting an electric shock if we touch it. Now, not all conductors are created equal. Several factors can change a material's resistance. First is the material itself. As we saw, copper is a better conductor than, say, iron. The second factor is length. The longer the wire, the more resistance it has. Think about it. A longer pipe means more friction and obstacles for the water to overcome. It's the same for electrons in a wire. Third, the cross-sectional area or thickness of the wire matters. A thicker wire has lower resistance because there's more space for the electrons to move through. It's like having a wider pipe for the water. This is why high-power appliances often have thicker cords. They need to handle a large current with minimal resistance. Finally, temperature plays a big role. For most materials, as temperature increases, so does their resistance. When a material gets hotter, its atoms vibrate more randomly and vigorously. These vibrating atoms get in the way of the flowing electrons, creating more traffic jams and increasing resistance. This is exactly why your phone charger gets warm. The resistance in the circuitry converts some of the electrical energy into heat energy. This conversion of electrical energy into heat is described by something called Joule's law. It's not always a bad thing. In fact, we use it all the time. A toaster uses a special wire with high resistance to get red hot and toast your bread. An electric stove, a hairdryer, and an incandescent light bulb all work on this same principle. They are designed to have high resistance to purposefully generate heat and light. So, from the copper wires in our walls that bring us power with low resistance to the insulating plastic that keeps us safe, and the high resistance elements in our toasters that make us breakfast, electrical resistance is a powerful and essential force that shapes our modern world. It's happening all around us, all the time. Thanks for watching. If you found this explanation helpful, don't forget to like this video and subscribe to the channel for more science explainers. See you next time.